Okay. So this class is going to be about algorithms. Um, so yeah, to like start off as the first question, what really are algorithms? Like, what is an algorithm?
Some process.
Okay. What is the process then? Someone has messaged on chat. A step of mathematical steps. Wow. So using step twice. Is there any a combination of mathematical steps? Okay. Um, That's an interesting way of thinking about it. How I like to think about it is somewhat similar. Yeah, you just like it's a series of like instructions, like do this, then do this, then do that. So if you look at like a more silly sort of thing, which is meant for like, I don't know, younger students, probably you'll see examples like how do you cook rice? This, then this, then this. This is an algorithm. But of course, in a more mathematical sense, it's something like perform this
मुझे
operation.
पूछा था मेरी एमसी की क्लास है स्पीकर हाँ
I think someone is on unmute by mistake. Oh wait, sorry, I did not mean to ask to unmute. That happens. Okay. Anyway, so yeah, the real answer which I like to give to this is it's really just a series of like instructions. Um, and the important keyword is not just instructions, but also a series of them. So it's like, do this. If this happens, then do this. If that happens, then do that. Like the way you imagine if you've ever studied some Python or Java or something like that. And that actually brings me to this very interesting thing, which is that algorithms really form the base of an entire subject, that is computer science. So the entire computer science is sort of based on this fact that you can teach a computer how to do something because you can like give it this series of instructions. You can tell it do this, then do that, then do that. Even if you're doing something like machine learning, which is not specifically telling it what to do, it's sort of generating things. But even then, it's really following the series of steps which are predefined, even though those steps might be something like go to this data set and understand that. Yeah, it's some sort of logical flow. Um, so the way I like to think about it is that algorithm is really a way of formalizing um, and a sort of operation. If you want to do something and you want to understand how you would do it in general, how I would think of it is, okay, what's the algorithm? So let's say, as an example, I know that x squared plus 5x plus 6, if I want to find the roots of this, I can factorize this and then I can do things. But if in general I have ax squared plus bx plus c, what's the algorithm to find the roots of this? What's the formula is somewhat similar, close word, not exactly the same thing. But how will I find the roots in general? How will I find the sort of instructions that need to be used in general? So that's one way of thinking about it. And the first very interesting question, which is not really related to Olympiad math in much of a way, but the question is that um, does an algorithm always exist? So um, this is an interesting question, actually. So first of all, what do you mean always? Um, the question is there really some sort of problem? Like you tell a computer that, okay, you need to figure this out. For any such problem, can the computer always, like, can you always create an algorithm to explain to the computer, do this, and hence you'll figure out whether the problem is true or false? That's a very vague sort of definition. But okay, maybe slightly more formal is something like, is there a problem where the computer needs to output either yes or no based on something, and there is really no algorithm which can like explain to it that this is the way you should decide whether to say yes or no. And I think the intuitive answer is that yeah, there should be an algorithm, like surely there is some way to do things, but the actual answer is no. um, as it turns out, there are cases when there is no algorithm. So one very famous sort of example of this is what's known as the halting problem. And I don't want to go into too much depth about all this, but the basic idea of this is quite funny. It's like um, the problem really asks you. So imagine like this is your computer, and you're asking the computer to say yes or no, and say yes if um, So what the input to this program, by the way, is going to be some code and an input into the code. So the input of this program is another program in some sense. So don't like overthink it, but the point is just that if that code plus input runs forever, that is like it goes into some forever loop or something like that. If you know what that is, like just some loop that just doesn't end or something like that, then it should, let's say, output no, because it doesn't halt. And if it does halt, that is the program does end, then it should output yes. And actually, there is no algorithm by which you can decide the halting problem. There's no algorithm by which a computer can decide whether this code will halt or not. And there's a really magical proof of this, which is like some sort of paradox. Like if this halting problem does have an algorithm, then you can create a paradox. Like there's a problem that should halt and not halt. Again, you can probably check this out on Wikipedia. But the real reason I'm doing this is just because it's a very interesting sort of topic and probably something like I feel quite excited into. So maybe something you can also talk. Um, but anyway, let's talk about
Wait,
some more
wait.
reasonable things. Yeah, someone was
Like,
saying something.
what happens when I put the halting problems code in the halting problem? Like, if it
So
exists.
the halting. So the point is that first of all, halting problem does not have a code. Like it cannot be created. That's proven. And if it did, then you can create a paradox, some sort of
Oh,
contradiction.
okay.
So like more specifically, like you can create this sort of program that should halt. But then if it halts, it shouldn't halt. And if it doesn't halt, it should halt. So like there's some sort of paradox that doesn't make any sense. So that's why like there are more formal ways of doing things. I think there are a lot of details and stuff like that, but this is the basic structure. Um, but anyway, moving on to some more Olympiadish things. In the context of math Olympiads, usually what an algorithmic problem will look like is it'll ask you, does there again exist, um, uh, like given something, can this be uh, done? Can this be done? And the answer will usually have two parts. So maybe it can be done, maybe it can't be done. If it can't be done, then you have to prove that it can't be done. Usually, the way you prove something can't be done is something like an invariant, like something is supposed to change, but it doesn't. So again, you can check out my class on invariants if you want, or some other class on invariants. But the topic of this class is that what if it can be done? Then you have to prove that it can be done. And the usual way to prove that something can be done is to construct an algorithm. So you construct the literal way, like this is how you do it. And like if you just tell them how to do it, then I mean it can be done. Of course, um, this is not always necessary. You don't necessarily have to construct an algorithm to show that it can be done. Sometimes there are these roundabout ways which just say that I don't know how to do it, but I can prove that it can be done. And those are a little more like they don't come up as often, but they're also really cool tricks. But yeah, so this whole thing is how it usually comes up in Olympiads that you need to prove that something can be done. And what's the best way to prove that it can be done? Like literally tell them how to do it, which is to construct the steps to do it. Um, and yeah, so the first question now is like, okay, sounds simple so far, but uh, yeah, double chess is a very interesting example of somewhere you know that something is going to happen, but you don't know how to prove it. So this is something I think covered in my class on comedy games. I'm not sure. Maybe I have. Maybe I haven't. I think Sai did cover it in her class. Not sure. Um, anyway, um, so let's actually do a little bit of a problem now. Okay, let me actually find the problem I've been looking for. Or let's actually start with this fun problem. So this is a fun problem. Um, okay, I didn't need to write fun in hindsight. But basically, this is like you have an n cross n maze. So you're given n, let's say it's a 100 cross 100 maze. And how this maze basically looks is it's a grid. But of course, all the lines don't exist. Some lines exist. So your maze looks something like this. Okay, I should probably not. Whatever. It's not the best maze I could have made, but there's some maze. You get the idea. So mazes look something like this, and you need to find some sort of path from, let's say, starting point to ending point. Let's say this is your ending point. So it's given that the maze is solvable. That is, there is some path from the starting point to ending point, which avoids all of these sort of roads. Not roads, I mean like walls. So unfortunately, you don't actually know what the maze is. You just know that it's in a 100 cross 100 grid, and some of these grid cells, there's a wall in between them, and you know that you start somewhere. You don't even know where you start. You just start somewhere, and you end somewhere, and you want to find a path from the start point to the end. And the question is, um, so give me a sequence of letters, U, L, D, R, so up, left, down, right. Um, just some sequence of this, so up, 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 left, down, left, right, 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 so on. So that no matter what my maze was, so I don't know what this maze was, no matter what it was, at some point during my sequence, I will have reached the end point. So you don't know what your start point is, you don't know what the end point is, you don't know what the maze is, but you still need to construct this sequence of up, left, down, rights, so that at some point during your sequence, you reach the desired end, no matter what it was. So basically, what the question is asking you literally is to construct an algorithm of moves up, lefts, downs, and rights so that you reach the end point. There's one detail that I missed. Of course, like for example, if your sequence is up, but there's a wall above you, then you don't move up, you just stay there. If you can move up, then you do move up, and then you keep going on and on in the sequence. So the question is, how do you do something like this? And if anyone has any ideas, like feel free to speak up. Meanwhile, I am just like finding my book's PDF so that I can take problems from it. Some message on chat. Ideally, it would be better. Okay, so yes, this is a good idea. Keep going up 100 times, keep going left 100 times, down 100 times, right 100 times. Repeat that. Okay. Can anyone give a reasoning on why this works or doesn't work?
It doesn't, because if there's like a cycle in the maze, we just keep going around it.
Yeah. So, for example, if what's the best way of drawing this? Yeah. So let's say you have something like this, and you start, let's say here, and what you need to do is go along this path. But what you keep doing is going up, then right, then down, then left, then up, then right, then down, then left. You never really think of going, like stopping in between. So if you are on the current path of just going right, you just keep going right till you hit this wall. So you sort of get stuck in the cycle. You never really go out as you're supposed to. So it's a very good idea actually to start with. That's the first idea even I would have had when I tried the problem. The next idea possibly could be something like try all possible combinations of up, left, down, rights, or something like that. But even that's messy, right? Like the point is you don't just have to construct the sequence, but you also have to prove that it works. So I can create some very complicated looking sequence, which um, I won't necessarily be able to check whether, okay, does this work or does this not work? But if I can't prove that it works, then it's probably not worth it. So um, an interesting way of thinking about this problem is when this is a very complicated sort of structure, right? This is like hard to think of. Like, how are you supposed to like concretely imagine what's going on when you don't know anything? You don't know what the maze is. Like, how are you going to do anything? So let's say I told you what the maze is. I told you that the maze is like this, or maybe just for the sake of this thing, it's just this maze. And I also told you the start point and end point. Now I think I can construct the solution, right? I mean, if the solution exists, then I can just try all possibilities until I find a way. And I mean, that makes intuitive sense that it should, if there is a solution, then just trying all possibilities will work out. And there are smarter things you can do. You can do what's known as a DFS algorithm, which is known for graphs, but we'll not get into that. The point is just that if I knew the exact maze, I knew the starting point and I knew the ending point, then all I need to do is like really just find that path. And that shouldn't be too hard. Like, not for, I'm not even saying for a computer, I'm just saying for a human, you just need to find it. So what you do now is, let's say you tell your computer. So you tell your computer that the maze was that maze, the one above, and you tell it this is the solution to that maze. And okay, computer remembers it, and let's say it even says out that sequence. But of course, there's very high chance that this doesn't work because this was not the actual maze. And then you realize, oh shit, now what? Um, Wall following, I didn't understand. But what I'm trying to say is that the whole difficulty of this problem is you don't know what the maze is. But you do know that there are, I mean, how many possibilities does this maze have? You know that it's a 100 cross 100 maze. So you know that there are only finitely many possibilities of like where the walls could be. It's a very, very big number. It's like 2 raised to 100 square or something like that. But it's finite. So there are finitely many possibilities for what the maze is. There are finitely many possibilities for the starting point, finitely many possibilities for the ending point. The point is that if I could, I can actually just list all these mazes down in a line, like just one by one. I can just list all of them down. And for each of them, I know how to solve that maze. So does anyone have any ideas now how we can complete this? So I now know that I can list all these mazes down one by one. I don't know which one in this list is the actual maze, but I know that it's in the list. And I know that for each maze in the list, how to solve it. Okay, someone has given me an answer. Label each box from 1, 1 to 100, 100 and write every permutation of possible paths from I, j to a, b after each code. Repeat the code reverse. Yes. So this is a very good idea. Now, basically, someone is saying that try for every cell to every cell, all possible paths. If there is a path, that then you should be able to do it. The only problem is that they're also claiming that these paths can be reversed, that is just go back the same way. But actually that does not work. Just because you could come along that path doesn't mean, okay, if you could come along that path, then you can return. But if you couldn't, because I mean, you got blocked at some point, then when you try returning, you might start messing things up. But that's very close to the actual solution. In the sense that, again, the idea is similar. The point is that we're going to try all possibilities. We're going to try all possibilities for the maze instead. And now the point is, let's say it's the first possibility. So we label these possibilities of the maze from 1 to 3 up till like, this is going to be some huge number, like 2 raised to 100 square into 100 square or some nonsense number like this. But it's a finite number. That's the only detail we're using. So the point is, if it's the first maze, I know how to solve that. So I'll tell the computer, do these sequence of moves. If it didn't get solved, then we know that it was not the first maze. So we'll try the second maze. And now the second maze, we know our starting point, ending point, etc. And we also know that because of this sequence of moves that we have already performed, let's say up, left, 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 down, we have gone a little far away from where we had started. But we'll just go back however we can because we know the actual maze. And then we'll go wherever we needed to go. And then we append that new sequence. So left, down, down, right, up, something like that. And if even this doesn't work, then we know that the second thing is also not the answer. And then we keep going down this list until the list is over. At some point, you must have reached. So what I'm trying to explain through this problem is that sometimes it's very complicated as to why something should work, like how algorithms should exist. But sometimes creating simplifications in the problem, like for example, guessing the maze, or like just like assuming that you know the maze temporarily, these things make the problem very easy. And really, what you need to do, um, a lot of times in combinatorics in general, is figure out how to merge a lot of these sorts of different ideas that you get. Someone is asking a question, does computer remember if path doesn't work? And even if command is to go again in that path, does computer ignore it? Yeah, so the second part, yes, if the command is to go up and there is no way to go up, then it's ignored. And the second thing, computer doesn't remember anything per se, but if it doesn't work, then I mean the sequence, like if it worked, then you terminate the whole process, like you won. If so, like if it doesn't work, then your sequence goes on. That's what I mean. So this was a bit of a convoluted example. It might make more sense to you if you think about it for like an hour or so. Like took me 1 hour to really get convinced that this works, but it's really an amazing problem. So I really feel excited by this one. So I wanted to start off with it, even though it's probably not the best problem to start off with in hindsight. But yeah. Um, I'm sorry for asking again, but is there no way to reverse or replicate a code allowing us to land back in the original position? So there is a way to reverse your code if you knew what the maze is. So if you know what the maze is and you know that you've reached this place by mistake, then you can go back. But if you don't know what the maze is, then it's much harder. And at least I don't see how. Um, it was like PHP sort of thing. Exactly. It's a lot like PHP because PHP also a lot of times we use the fact that things are finite. It's a very big number, but it's finite. One very interesting thing I want to highlight about this problem is that it's terribly what is known as inefficient. Um, so inefficient is basically this way of saying that no one in the real world would do this. Like no one in the real world is ever going to work with 2 into 100 square things. Just to give you an example, 200 to 100 square is probably, I mean, I'm at this point I'm guessing, but I think it's probably more than the number of atoms in the observable universe. So a very high chance. Actually, yeah, that is just true. That is just true. I think the atoms in the observable universe is something like 10 raised to 80. And this is like this is like 8 raised to 16 raised to 2500. So much more than 10 raised to 80. So like no one is working with this. But the point is that when we're in maths, we don't always care about whether the algorithm is efficient. When we're in computer science, sometimes we do. So that's why one important part of these algorithms often becomes obviously there is some algorithm, but what's the best way to do it? What's the most efficient? What's the way that takes the least steps? So this does not take the least steps that I can tell you. But it's an algorithm. That's all the question asked us for. So yeah, some more questions. What's the use of algorithms in Olympiad combinatorics? So, as I mentioned a little earlier, and like a lot of times the Olympiad problems look at something like you're given something and you want to, and they ask you, can this be done? And so if the answer is no, then you can do some invariant stuff. If the answer is yes, usually the solution is just construct this algorithm. So that's where it really comes into Olympiad problems, and those are the sorts of problems we'll now see. But I will need about 2 minutes because my thing is not loading. Um, just give me a minute. Okay, seems to be loading now. Uh, if people want a sneak peek into my book, I can show that. Uh, if I can figure out how to change the share. Uh, actually, actually, that might be illegal, so I won't do it. Uh, yeah, I'm not sure what contracts I've signed. whether they say whether I'm allowed to share my books PDF and stuff. Okay. Yeah, I'm just taking some problems for it. Just give me a minute, guys. Meanwhile, does anyone else have any questions? Can you people please speak up, by the way? Yeah, so I will not probably do too many problems um, from the example sections of the book. If I do problems, they will mostly be from the um, other section, except for like one problem, which I think is really worth doing, just so that everyone is clear. This book is a book called An Exploration of Olympiad Combinatorics. It was written by me, and it's available on Amazon if you're interested. Okay. So, yeah, someone has raised their hand. Go ahead.
I have got a question. Like, can we like guarantee like each sequence is a cycle? Like after each sequence, we like start off in a new sequence to see if it works. So are they like all cycles? We start at the same point again.
I didn't understand. Can you repeat?
We take each sequence to see if it like works in the maze. So are
Okay.
they like all cycles? We start off at the same point again.
Um, no, I'm still not understanding. What is the question? Like, sorry, I'm a bit confused.
Then could you explain the algorithm again? Then I think I misunderstood them.
Yeah. So, just to explain again, what we're basically doing here is that we're taking every possibility for the maze, and given a certain possibility, we know how to solve it. Like we just see the maze and we see the directions we should use, and we write that down. Then, if it doesn't work, we move on to the next thing in our list, and we see like currently we have already made some set of moves. So where has that taken us? Then we reverse those moves so that we come back to the starting point. That's not actually very necessary. But the point is, from there, you go back to the ending point. And if you still didn't finish, that means that it wasn't this third maze either. So then you move to the fourth maze in your sequence and so on. Okay. So
Okay,
this is
I
the
missed
only,
that reversing part actually.
sorry?
I missed the reversing part. Like if it doesn't work, we
Yeah.
reverse it.
That is an important part because otherwise it gets really weird. So yeah, this is the only problem I'll really be doing from my book. It's the first example. Um, but and sorry to people who have seen it, but I really want to talk about some sort of motivations in relevant to this. I don't really want to talk about the solution itself. So I think even if you know the solution, it may not be too helpful. Um, yeah. So this problem is basically saying that you have this m cross n grid of positive integers, and you're allowed to either subtract a single number from all things in a single row or double everything in a particular column. And you want to show that these two operations can be applied in some order so that all the integers end up as 0. Okay, and just for my information, it's sold out on Amazon. Is that true? It's crazy. Yesterday there were 30 copies available. If it got sold out today, like that's concerning. A lot of copies. I don't know. Okay, we can talk about all this after the class. Um, but yeah, this is a problem here, and the problem is interesting. Like the first things I want to talk about this problem is that there are some unknown variables. There's this m, there's this n. And the first thing you should really do sometimes when you don't know m and n is like take some example cases. Because it's sometimes very hard to sort of judge a problem or understand a problem if you're working very generally. But if you're working with a specific sort of example, like m cross n instead of 3 cross 3 or a 2 cross 3 even, those things become a lot more simple to deal with. In fact, the first thing you should maybe try to start off with is a 1 cross 1. And that turns out to be a bit silly because 1 cross 1, just the point is that you can subtract whatever the number is from that number. Like the first operation just allows you to subtract k from that number if the current number is k, and you can just make it 0. So you're done. So 1 cross 1 is a bit silly. let's try a 1 cross n in general. Or rather, in even an n, we'll try a 1 cross 2. So you have two numbers like this. And in a move, you can either subtract the same number from both of them, or you can multiply one of the numbers by 2. So let's say you have like 3 and 5, and you want to make both of these 0. So can someone give me an example of how we could do this? Okay, someone has given some ideas. 1 second. Observe that if all numbers in the board become equal. So yeah, so someone has given this idea that we should try and make all numbers equal. That's obviously very good, because if all numbers become equal, we can subtract this common integer from all of them and everything becomes 0. So the main difficulty of the problem, of course, becomes, can we make all numbers equal? Someone has also given this idea, make one number 1. So that's an interesting question. So interesting idea. So let's actually just take the case. Can we solve this problem if there was 1 and 10? How do we work with this now?
I don't think we can.
We can just double the one, like it in the column one, except when nothing is there. So we can double one and then subtract like one and repeat that again and
Yeah.
again.
So the way I like to think about this is that there's really only one option that you have. If you try to subtract a number from both of these, then this number becomes, let's say you subtract 1 from both of these, this becomes 0 and 9. And now there is really no way of reducing this number. If you try to reduce this number any further, this number will become negative. And if a number becomes negative, then you can either make it more negative by subtracting a positive integer, or you can double it, which also makes it more negative. So you can never increase it back to 0. So subtracting a number will make you doomed right now. Doubling this 10 looks stupid because, I mean, 1 comma 20 is just worse than 1 comma 10. So like really the only option you have is maybe make it 210. And that gives you this very interesting idea, because now you can subtract 1 from both of them and it becomes 1 9. And this is now some sort of induction, right? 110 has reduced to 1 9. Similarly, I can now double the 1 again to 9, to 1 8, to 1 7, and so on. Until finally, let's say we reach 1 comma 2. And then I double this again. You get 2 comma 2, and then you get to 1 comma 1, and then you can just go to 0 comma 0. And we're happy. So if the first number is 1, we're done. If it's not 1, if it's something like 3 comma 7, we can just make one of the numbers 1. We can subtract 2 from both of these. So we can just make it 1 comma 5, and then we're happy. Because we can make this 2 comma 5 to 1 comma 4, 2 comma 4 to 1 comma 3, 2 comma 3 to 1 comma 2, and so on. So that's already a lot of non-trivial stuff we did here. Like the problem was asking us to do for like general m cross n, but even solving it for a 1 cross 2 was not trivial. Like it took us a little bit of effort. So that tells us that like the way I think of it is that if a certain base case is too easy, it's not really helping you at all. And if it's too hard, it's probably not worth it. But if it's somewhere in the middle where it took you a little bit of effort, but you could do it, that's probably telling you how to solve the problem. Like this is the sort of thing which you probably now need to look, how can I generalize this in more dimensions or more things? So what really happens if you work with the 1 cross 3? So you have 3 numbers now and a single row. Some people are giving more ideas. If we can make any one of them 1, then repeat the process. I think that makes sense. So let's assume again that one of the numbers is 1, and let's say this is 6 and 7. So just gaining insight from our previous example, what we could try and do is double this 1. You go to 2, 6, 7. And then you subtract 1 from all of them, and you reach this sort of simpler scenario of like 1, 5, 6. And then you can repeat this to go to 1, 4, 5, 1, 3, 4, 1, 2, 3, 1, 1, 2. And that's where you need to start being a little careful. So you reach 1, 1, 2. And what you need to do now is be careful, because if you multiply this by 2 again, it becomes 2, 1, 2. And then if you subtract 1, it becomes 1, 0, 1.
You
And
can
this
just-
is bad.
Why can't you just multiply both of the ones with 2?
Yes, that's what you should do. So you should multiply both of these by 2. It becomes 2, 2, 2, and then you're done. So how would we say this in general? What exactly are we doing? So our step one seems to be make a number one. That's easy. Make at least one number equal one. That you can do by just subtracting like the min minus one. So if the minimum number right now is 5, okay, 5, 8, 11, just subtract 4 from all of them. So one number becomes, that's cool. So now you have something like 1AB. And now our process seems to be saying something like, and let's assume like A is less than B. So it's something like multiply this by 2. So you go to 2AB and then go to 1A minus 1, B minus 1. And keep repeating this until you get to 1, 1, and some B minus A plus 1 or whatever. Some number. We don't even care what it is. It's some X. And then what you do is you multiply both of these numbers by 1 now. So you get 2, 2x. And then you make this 1, 1, x minus 1. And you repeat this until you get to 1, 1, 1. And then you subtract 1 from all of them. It becomes 0, 0, 0. So that was a bit complicated, but it makes a lot of intuitive sense, right? So what we're really doing is we're making one number 1, then we're making the number after it 1, and then we're sort of clubbing them. Then we're making a third number 1, and then possibly if there were 4 numbers, make a fourth number 1, and so on until a lot of things become 1, and then we subtract 1 from everything. So is there a better method, as this takes many iterations? It's a very good question. I'm almost sure that there is, but it'll be a lot. In fact, I can already think of some methods which are faster for a 1 cross 2, which are based on some sort of binary based approach. Like 1, 10, for example, it was very inefficient what we did, make it 1, 9, 1, 8, 1, 7, etc. What, for example, we could do is like do 8, 10, and then it becomes already 1, 3. And then 1, 3, you can make 2, 3. So you speed things up a lot. But we again don't care about that. This inefficient word like really doesn't exist over here. So we don't care. What we are actually looking for is the most generalizable algorithm rather than the fastest one. The one that we can really think about very simply. Something that makes a lot of intuitive sense. So yeah, someone has, I think I got the general idea for M comma N. And yeah, I think your idea does seem correct. So yeah, actually that is exactly correct. So that is it. And in fact, we are also almost there actually. It is possible that the general solution is different. Yes, of course it's going to be different. But my point is that usually the solution's motivation, the idea of how you're going to come up with the solution for general M comma N will be based on how you do it for a 1 comma N. So now on that note, let's actually understand what happens in a 2 comma 2, just to gain some insight on what happens when you vary M. And now what your operations are subtract something from a row, like subtract k from a row, or multiply an entire column by 2. So I think some people have already got this on the chat. And the idea is quite simple. The point is, think of it as only the first row temporarily and work with it normally until you make both of the elements in the first row 0. And the funny thing is now these numbers will just remain 0 because I'm only going to subtract numbers from this column. I'm never going to hurt this column. The only thing that could happen is I'm multiplying things by 2, but 0 into 2 is still 0. So these numbers will just stay fixed as 0. And these numbers also I can just work with the same way until they also come to 0. So actually, if you can solve the problem for a 1 cross n, it's very easy to generalize that to a 2 cross n, 3 cross n, and so on, because you just solve it like sort of one row at a time. Yeah, just induction. So just the point is like you just make all of these 0, and now you just forget about that. It just doesn't matter. But there are still some things we should be sure, like how exactly do we do it for a 1%? And I think now it's sort of making intuitive sense to everyone. So for example, can someone tell me how you would do 5, 3, 5, 8, 10? What would be the algorithm to do this? if someone is feeling like talking about it. Okay, so first step someone has given as a -2. So we go to like 1, 3, 6, 8. And I think this is a very good way of formalizing your things. Just take a slightly complicated example, not too complicated, but something that is not like a base case. And if your sort of intuitive algorithm works in that case, then it probably works everywhere. So yeah, now someone is saying make this a 2, 3, 6, 8, and then subtract 1 from all. So this, oops, this becomes 1, 2, 5, 7. Then do that again. 2, 2, 5, 7. Subtract again. 1, 1, 4, 6. And now the new part of the algorithm starts. So you start multiplying both of these by 2, and then again subtract. So 1, 1, 3, 5. 2, 2, 3, 5. 1, 1, 2, 3. So on until you reach like 1, 1, 1, 3, or 2. I don't know. Yeah, 3. And then you again do this 2, 2, 2, 3, 1, 1, 1, 2, 2, 2, 2, 2, 0, 0, 0, 0. And that's it. So the idea is just like until two numbers become 1, you make the second number 1. Once two numbers are 1, you make the third number 1. When three numbers are 1, you make the fourth number 1. Once all of them are 1, all of them 0. Clean enough. So the way I like to think about this is if you try to start off with the 8x8 or something, you're going to get quite screwed. Like you will probably not be able to solve the problem for a fair bit of time just because things are so complicated. Like it's just very hard to think about. But if you start with a small case where things are more intuitive, things are simple to think about, that gives you a lot of intuition about the problem. And even if the algorithm does happen to be very different for a general ampersand, um, there's still a lot of intuition that you can get. Exactly. The moral is to experiment with the simplest case. Okay, the simplest case here was a bit silly, but the second simplest case. Yeah, so in general, experimentation is really important in combinatorics in general, but also in algorithms specifically, because the problems here are sort of that sort of thing where you just need to keep trying a lot of different ideas. Like you don't necessarily know what the right sort of algorithm is. Is the best way to do this just going straight, or do you need to sort of find a convoluted path? But sometimes this experimenting will give you that sort of answer. So yeah, now let me think about what problem we should do. We can do something from the exercises of chapter, or we can do something that's not in by. Oh, we could actually do the IMOP5. I hate that problem, but we could do it anyway. Yeah, that problem is how can we write the solution to be complete? That's a very good question. So actually, I'll actually talk about that. So I think one of the major problems in combinatorics happens for people is that it's very hard to sort of formalize details. You're not very sure on how should I write this up. So it's important to figure that out. So I think the cleanest way to write things out is to break things into steps. So so first, let's say show it in parts. Like the first part, I think I will say for a general m cross n, first I'll show that it's equivalent to solve it for a 1 cross n, because if I can, I will just do that one column at a time. So I will just prove that once a column is 0, I can make sure that it retains itself as 0. I'll just like write that down because multiplying by 2 will not affect the zeros, and I'm anyway not going to subtract anything from that column, from that row. So now it's equivalent to solve it for a 1 cross n. So that's one. Now the second thing I'll say is now here's the steps to solve it for a 1 cross n. Step 1, make a number 1. Step 2, until the second smallest number becomes 1, keep doing this. Once the second smallest number becomes 1, multiply the first 2 by 2 and repeat. And in general, if the k smallest numbers are now 1, multiply all of them by 2 and then subtract 1 from all of them until the k plus 1 smallest becomes 1 as well. And do this until all numbers become 1 and then all numbers become 0. Like literally just write this out. It's important that you actually write these details out, because sometimes what happens is people just like skip a lot of details. They just write, hence it works. But that can be a bit risky, because even if you know what you're doing, you also need to prove to the examiner that you know what you're doing. The good thing about an algorithm is there is no real proof per se. A lot of the times, like I mean, I'm just telling you it works. Like you've reached 0, 0, 0, 0. So it worked. So there's nothing to prove per se, but you need to make sure that your algorithm is very clear, that everyone understands what you're trying to do. And then you shouldn't run into issues. That's clear. Does anyone want to say something?
We can write the proof as you say.
I think someone is on unmute by mistake. Yeah. Okay, let's try some other problem. Huh. I don't really know which problem we should do. Okay, let's do this. I think today we're doing all hard problems. But I think hard problems are very useful in just trying to understand and gain intuition. Like when you're practicing, it's okay if you're not doing things that are a bit too hard, because then like it's also a bit demotivating and stuff. But especially when you're in a class and you're trying to learn something new, it's very useful to do a lot of hard problems.
And like this year's IMO P5.
Sorry, this year's IMO P5, what about it?
You're telling like problems like this year's IMO P5.
Yeah, so this year's IMO P5 also we could discuss, but yeah, I just don't like that problem. So I don't want to discuss it. I did solve it, but I just don't like it. Like it's a very meh problem. Like it doesn't excite me. This problem on the other hand, like really excites me. Like it's a brilliant problem. Was the solution the same? Yeah, it was broadly the same. I mean, some slight differences. Like I didn't actually scan through the entire top half of the grid. I just walked along the diagonal because that's also sufficient. It didn't take me a lot of time, only like 15-20 minutes. But the point is that if you get stuck onto the wrong idea, then you're not solving it. If you get the right idea, then you're going to be done fast. So it depends a bit on that. We could actually discuss it because it does give some sort of intuition. But yeah, maybe after this point. Was it sufficient to see the diagonal thing? Yeah, it was. That's why I got the points.
How much it took it for you?
Sorry, how much?
Time.
It took me, as I said, around like 15-20 minutes to solve it. It was, I did it quite fast. Like I got a bit lucky. Yeah, oh sure. Okay, I will discuss it then. If since people are quiet.
Orientation in the question.
Sorry?
What does orientation mean here in the question?
Right. Let's read the question. We are playing a game with the devil, and coins, heads and tails. Whenever the rightmost coin is head, you decide it's new. Yeah, so new orientation is just heads or tails. So the basic point is that you have these coins, let's say 4 coins in a row. Each one shows either heads or tails. Let's say heads, tails, heads, heads is the current thing. If a coin currently shows heads, the rightmost coin currently shows heads. So I get to decide what to do with it. Let's say I choose to let it stay heads. And then I remove it from here and I put it at the leftmost. And again, the next one is again heads. So I can choose what to do with it. I move it to the left. And this time, let's say I make it tails. And then it's tails now, the rightmost coin. So whenever the rightmost coin is tails, the devil decides what to do with it and moves it to the left. So that now I don't have control over what the devil is doing, but it does something with this coin and moves it to the left, either heads or tails. And then this process keeps going on until hopefully all the coins face the same way. So until all the coins face, in fact, if all the coins face head, you can make all of the coins face tails after some time. So that's but whatever. The point is just you want all the coins to eventually face the same way, no matter how the devil works. Who starts? It could matter. So that's the point, right? You don't know the starting configuration. It could be anything. It depends on what the starting configuration is. If the starting configuration has the rightmost coin as a head, then you start. The rightmost coin currently is a tail, then the devil starts. You can currently avoid this 2 to the n thing. Like, we'll just try to find a strategy, and then actually it's going to be quite obvious as to if a strategy exists, then a 2 to the n move strategy also exists. But that's not the key part of the problem.
I don't know, but why I am little tempted to assign numbers to each of the orientations, like tails can be 0 and heads can be 1.
Yeah, that's a very good idea, actually. That shows a lot of intuition, because that's something that you should always try with problems which have heads and tails or something like that, because that's a very common idea that you want to just, first of all, it makes life a lot easier. Instead of drawing circles and H's, I can just write ones and zeros. So that's easier for me. And also, like, I don't know, sometimes it does turn out to be useful. So for context, this doesn't change anything, but now I'm just treating all heads as, let's say, zeros and tails as ones. And I want to reach all zeros or all ones, one of them. Someone has given an idea. Game is basically so that we must so what you're saying is that there are 2 to the n possible strings here, of course, like this is binary. And you're saying that we can try and reach all possible configurations, but the question is why? Like, what you're saying is we must try to create a new sequence, but like our only options are moving the 0 to the start and choosing whether to make it a 0 or a 1. But what if both of those sequences have already been seen? Basically, the problem which could happen is, which is the scary part, is you run into some sort of loop. So you try doing something, let's say this is the thing, and you try making it something, and then the devil chooses to make something, then the devil gets another move, then you choose to do something, you choose to do something, the devil does something, and you come back here. And then you get stuck in this loop forever. And you never, and actually like 0, 0, 0, 0, and 1, 1, 1, 1, 1 are just like outside this loop. So you never actually reach it because your algorithm is just telling you to stay within this loop. So what you could, of course, do is try and break out of the loop. So try and do something else over here. But what if you get stuck into a second loop? So these are the things that are a bit scary in some sense. But yeah, this is what we really need to work with.
For
Induction.
example, I would like to give an example for the loop. If it was like 0, 0, 1, then the
Okay.
devil of course wouldn't want it to convert it to 0, 0, 0. Then it
Yes.
would give 1, 0, 0.
Yes.
And now if we continue to remain at 0, then
Yeah.
again we'll
Yes.
be stuck.
So this is actually a very good point. The most intuitive thing to do for you is to keep all your heads as heads. Because, like, I mean, of course, right? Like, I only get to control something when it's a heads. So, of course, I should try to keep my heads as heads, because then otherwise I'm giving the devil more control. That's not a good idea. But if you, like, don't change anything, then the devil won't change anything either. The point is, like, you have to move this here now, and by our strategy, yes, you should probably not change a heads into a tails, because that's giving a devil more opportunities. And but then you get, like, this is the same as this, right? So you get like stuck in this loop.
From 1, 0, 0, it's done now, because 0 to the left will become 1 and 0 to the left will become 1. So it's 1, 1, 1.
Yes, yes, exactly. So in some cases, you do have to like sort of look for the greater good, even if it feels like you want to keep your heads as heads and keep control of everything. Sometimes the right thing to do is just to make more tails. And exactly, so 1, 0, 0, you can move this thing over here and make it a 1. So it's 1, 1, 0. And again, you get to move this here and it becomes 1, 1, 1. But how do we do this in general?
Just can you tell us which is head and which is tails? Like 1 is head or 0 is 0 is head?
0 is heads.
0 is head.
So you control the zeros and the devil controls the ones. So actually, once you reach this 1, 1, 1, now the devil has total control, but it's too late. The devil has already lost. Everything is the same. So in particular, what this tells us is that if you have the sequence 1 0 0 0 0 0,
Yeah,
this is
it's done.
this is
Done.
done because you can just keep doing this 0 0, all convert all of these until you reach all ones. So that's a good idea. Okay, someone has given the idea of trying small cases with 2 3 4 5. That's a good idea.
I think weak induction should do it.
So someone is also giving the idea of induction. Yes, I think induction is a great idea. In fact, there is a solution with induction, but it does take a lot of careful effort. So we will also talk about it. But instead of looking at what I would call a hard technique, so the way I think I've seen Evan put it is there are two sorts of techniques. There's soft techniques and hard techniques. So soft techniques are things which are just like trying to understand the problem, trying to gain intuition about the structure of the problem, trying base cases of the problem, things like that. And hard techniques is actually trying to use induction or something. So usually it's better to first experiment a bit and then start working with your hard techniques because then you have the intuition of what should work and what should not. So of course, induction might be the final step of the solution, but it's probably not the first way of thinking about it. Even though your solution will probably start with let's induct, doesn't mean it's the first thing you need to do. So yeah, let's try some examples with 1, 2, for 2 coins, let's say. So there are only 4 possibilities. So 0 0 you're already done, 1 1 you're already done. If it's currently 0 1, then it's the devil's turn. If the devil makes
What
it a
is
0, he loses. If
yeah,
not,
and
we reach 1 0. And
if
then you can just make the 0 a 1. Right? Does this make sense?
yeah, and at 1-0 we are already winning.
Yeah, and 1 0 is equivalent to this place. So yeah, 2 was not very helpful in terms of intuition. Maybe we should try 3. So this 0 0 0 1 1 1 is done. We also know how to do 1 0 0. We also know how to do 1 1 0 because again we can just move this here. Now it's so these 4 are easy. And this is also interesting, like what sort of configurations are easy? Now the point is I don't necessarily need to reach all zeros. I just need to reach one of these configurations because from there I know how to finish. So that's also an interesting way of thinking about things. So let's say things are 0 0 1. Now this is also easy actually because the point is the devil has to make the first move. If he makes it 0, he loses. If he makes it 1, which it already was, then you've reached something that you know how to handle. So that's fine. So even 0 0 1 actually we can put into this set now.
Just a question. Should we worry about that construction of 2n moves while we are looking for
2 to
this?
the n, no, you should not because like I've told you that, I mean, in an actual contest, you should probably worry about it. But for now, in fact, we'll just solve the problem generally. We'll not even try to find how many moves it takes. And actually, there's a very neat argument which just proves directly that if there is an algorithm, then it has to take less than 2 to the n moves. So that is not very hard to prove, but we can deal with that. So what other cases? What about 0 1 1? Or maybe let's start with 0 1 0. Yeah, this is actually easy because you just make this 0, put the 0 over here, so it becomes 0 0 1. And again, it's something we've seen. So repeatedly, we're just trying to push things into our sort of known configurations. And honestly, so far we have not really gained too much intuition. We're just doing what seems to be the most obvious move. And it's a bit vague. We're not very clear on how to do things in general, but at least we're gaining some insights. So, but that was interesting. What about
We can say
consider
that
the cases with 0 at the end, like after the devil has made all his moves? That's a good point. No, actually, on the contrary, we should probably consider all the cases where the thing is not 0, like the last digit is a 1. Because if the last digit is a 0, we can just push that here and make it a case where the last digit is 1. How would one determine the number of good configurations for any arbitrary n? So the question actually asks you to prove that all configurations are good, as in like from any starting configuration you can. Oh, easy. Um, yeah, so we don't currently know any way to do that. We have no idea. We're just like experimenting. We're in the experimental phase. And it's important to note that your experimental phase will not always help you directly or fast. Like, I don't think anything we've done so far has actually any impact on us solving the problem. But it just starts giving you a little bit of confidence, right? Like you're gaining some sort of idea of where to start, how to do things. So yeah, so let's try this one maybe. This is, I think, the slightly most complicated example because there are a lot of possibilities for what happens.
Uh, Maybe I was also talking about this number. If we can prove for some small number that it is like one where ones are continuous and zero are also continuous, then maybe we can try some induction process and prove it for some larger cases when ones are continuous, and then
Hmm.
prove that every number can be created into such ones continuous and zero continuous.
Yeah. So one thing that a lot of people try to do when they try this problem, at least like from what I've seen, is they try and prove that the number of blocks of zeros, like if you try and split the numbers into blocks, something like this. Um, the number of blocks of these things they try and keep reducing until it becomes just a single block. Now, this is obviously an amazing idea. Like it makes a lot of sense. But as far as I've seen, it's not very easy to make this work because just whenever it becomes the devil's turn and he's working with this series of 3 1s, he's going to ruin your life. He's going to make it 0 1 0, and your blocks have increased by a lot. So, but of course, that's still useful in the sense that I think what you were suggesting was something like if you have, let's say, all ones and then all zeros, how would we deal with? Okay, this is easy, but like, for example, if all zeros and all ones, like this. But this is a bit messy because we don't really have control over this. Okay, actually, now that I think about it, I think someone was suggesting on chat that you're right. The devil, we should let the devil make his moves first, and then like consider all the cases where zero is actually at the end. So even that does make sense actually to me now. Um, but I think what I am realizing by just trying some of these examples is that this is really not helping. Like, I mean, last time when we were doing these cases, we were gaining a lot of insight, right? Multiply the smallest number by one, keep reducing, etc. Now what we're really doing is just like, I mean, do something like, oh, we can reduce to this case. Oh, we can reduce to that case. But that's very random. There's no general sort of feeling that I'm getting from all of this. So that probably means that what we should do right now is maybe take a little bit of a step back and think about um, stuff generally. So
Can
this is a scary. Yeah, go ahead.
can we try to increase or decrease some number in binary?
That's a very nice idea. So of course you have numbers in binary here, and it makes a lot of sense to sort of think about what that number is. Um, and the sort of problem with it at the start would be that, I mean, it's changing very rapidly. For example, if the starting number currently is a zero and you push this over here, this becomes a one, suddenly the number has increased by a lot. And if you did something else, then it could have reduced by a lot. But there are ways to work around these things. Um, okay, someone has said some.
One thing can be like the winning position for us is reaching the maximum or the minimum number. Like
Yeah,
0 0 0
yeah.
is
But actually,
minimum.
you don't really like that, right? So if your strategy in terms of binary is that you keep increasing the number, you keep decreasing the number, doesn't make sense that you should end up at one of the maxima or minima. You should end up only at the maxima or only at the minima. So, okay, someone has said this. We are holding the devil hostage. H is advantageous to us, and although devil has control over T, if he switches to H, it's actually good for us. Very good. So the point is that we like to keep things H, but if we keep everything H, the devil keeps everything T. So at some point, what we'll have to do is make some of our H's a T, so that the devil becomes scared that if he doesn't do anything, everything becomes T. Does that make sense? So the point is that if I keep all my heads or all my zeros as zeros throughout the process, devil will keep all of his ones as ones. No one is making progress. On the other hand, if I start making all my zeros as ones, then the devil is going to start getting scared. Oh shit, if I don't do anything, then he will convert it to all ones, then I'm screwed. So he will start having to make some of his one zeros, which we might be able to use in some. So going back and mixing up some of our ideas. Um, what we'll do here is think of the problem in a slightly different way, which I think um, makes a lot of sense to me at least. The way I like to think about this problem is instead of like moving the coin all the way to the left. Okay, someone has a, uh,
I've
Sharanya,
got a
go ahead.
question.
Mhm.
Yeah, so basically, so we're gonna change all of our heads to tails. So in like it could like scare the devil, and it could like also play advantage to the devil. Like
Of course,
he could
of
like also
course.
take advantage to it.
But really, it's our only choice. Like we don't have the choice of keeping all our zeros as zeros because then we can't win. We know that the only way we could win is if we do something which seems suboptimal. So, like, of course, we don't always do that. I mean, that would be a bit stupid. But in some cases, that might be the right thing to do. So we have to sort of let go of this bias that, of course, the right thing to do should be to keep our zeros as zeros. And maybe uh, doing suboptimal thing is always overall suboptimal. No, not true. Doing suboptimal things over a long time might make it optimal because doing optimal things over small periods, um, I don't know. I don't know what I'm saying. But the point is that it's not always the right thing to just do what looks obvious. You have to maybe think more long term.
Also, one more
Suboptimal.
question. Uh, yeah, one more question I have is that which will give us more advantage, converting all to zero or all to one?
So both are equivalent in terms of like if either happens, we win the game. But an interesting thing to think about is that if everything becomes zero, we have control over everything. So we can make everything one after this. So eventually you can just prove that, like the question could have been prove everything becomes one or everything becomes states at some point. So in terms of advantage, there's no real advantage, but yeah. Yeah, that's what I like to call a greedy algorithm. So the greedy thing to do is to maintain each of your zeros as a zero because you want to maximize the number of zeros so that you have the maximum amount of control. So the greedy thing to do would be to keep your zeros as zeros. But that doesn't work because the devil also does that and then you make no progress. So we have to look beyond this sort of greedy thing and think about what could be the best long-term solution. Okay, so the ideas so far which I've liked are binary, because that's something that's very useful. Induction, because that's also something that can come in handy a lot. Um, what didn't work out here, sadly, are working with base cases. Although what that did tell us is that some things don't work. For example, keeping all your zeros as zeros won't work. That sort of intuition is important. And in fact, it's integral to solving this problem. Um, so now we need to really come together and think about how we sort of make this work. Um, so let's say you do have this number, and instead of moving things all the way to the start, which feels a bit weird, what I'll say is that first you check this number. If you want, you flip it. If you don't want, you don't flip it. The devil does that. Then you go to this number. So it's really like you didn't shift it. Instead, you just moved your cursor instead. And then you do it with this number, then this number, then this number, then this number. And then, so instead of like thinking of the rightmost at each point, you just change your definition of rightmost along the whole thing. So now the number is really just, now it sort of starts making sense that you want like a binary number to increase or decrease or something like that. What does not make sense anymore is like how you would sort of think of the rightmost element. It's not about that anymore. Can we use a monovariant? Exactly what we're trying to use. We're trying to increase the binary number or something like that. Yeah, so the following structure is easier to work with. This is why I did this when I tried the problem first time. Like it just felt like moving the coin around makes it a lot harder to for me to think about the problem. Whereas if you think of it this way, then it's like one thing that you can do is you can think about an entire round. Like you went through all the numbers, um, and now you're back. And over this entire round, something good has hopefully happened. Like hopefully the binary numbers, let's say, increased. That would be optimal for us. So something like that. Can you repeat the algorithm? There's no algorithm per se yet, but the point is that I'm just restating the problem. Instead of changing the rightmost thing at every point and then moving it to the leftmost point, I will first change the rightmost thing and I will change this one. So instead of moving this here and then changing this one, which was the rightmost thing, I'll just not move it there. I'll keep it here, but I'll just work with this one, then this one. So more like seeing it globally than locally. Not exactly. I think um yeah, okay, that's some way of thinking about it. The way I sort of think about it is just like what's the sort of simplest way to think about this problem. It's uh, like global is usually not the easiest way to think about the problem. Local is the best way to think about this problem. Like think about, I don't know. Yeah, changing cursor is a bit vague. Um, I don't know. Like the point is just your cursor is over here and you're changing this number. And now after this, you should be changing the second rightmost number because the rightmost number has moved to the leftmost position. So instead of moving this number all the way there and then working with this number, we just let it stay here temporarily. But we move our cursor here and we change this number. And then now both of these numbers would have moved here, but we let them stay there. We work with this, we work with this, we work with this until it happens that this number, which would have been equal to that number. So then that's why our cursor comes back. Each step doesn't work. Yeah. That's valid. So that's a fair way of thinking about it. Instead of thinking about it one step at a time, you're looking at a whole round. Okay, so yeah, now what? So let's say we do have some number. Let's say we have 1 1 0 1 0 0 1, and we'll end at a zero. Let's say. So let's say I like my zeros, I'll keep them as zeros. But then the devil says, ha, I like my ones, I'll keep them as ones. And then we make no progress. So that's not very useful to us. Okay, that did not go anywhere. We just came back. Nothing changed. So what I realize is, okay, if I need to make progress at some point, decrease the number of digits with different neighbors. So this was something also I mentioned at some point actually. Um, you're trying to actually minimize the number of blocks, sort of like blocks of ones and zeros. It's equivalent to what you're saying. But the problem is if you ever get a block of ones, the devil can mess you up completely by making this 1 0 1 0 1 0. And then the number of blocks just increases by a lot. So those sorts of things are messing up. But coming back to this, what we can do here and what we really have to do is we're going to threaten the devil. So we're going to say, I'm making this one. Now it's your call what you want to do. And the devil is like, okay, good for me, you made it one. I'll keep my one as one. Then you say, okay, I'm going to threaten you even more. I'll make both of these also ones. And let's say the devil is like, again, okay, big deal. I'll keep my one as one. But then you just make this also one and you win the game. So the devil is like, wait. Let me go back a bit. So the devil is like, okay, so maybe instead of letting this number stay one, which is what I did, and then you could change the last zero also to a one. What I can do is I can make this one a zero. And now you are a little bit messed up. Right? But let's go back to what the original number one was, by the way. It was 1 1 0 1 0 0. No, wait, what? Yeah, 0 0 1 0. Okay. And now the number is this. And now let's say I just like, okay, I'll just keep my zeros as zeros. He keeps his one as one, whatever. The point is that this one, like you forced the devil to make some change over this round. If the devil did not make any change in the entire round, then everything, all the zeros would have become ones and the devil would have lost. So the devil at some point was forced to make some change. And when the devil made that change, the devil made a 1 a 0. So in terms of binary, they sort of reduced this thingy. And after that, everything really stays the same, because after that, I can just say that, okay, now whatever zeros are there, I'll let them stay zeros. If the devil wants to make a 1 also a 0, good for me. Otherwise, doesn't matter. But my point is, if you consider these two numbers, this number has sort of reduced in binary, because this like this part is really irrelevant. This is all irrelevant. The point is this one has become a 0. So no matter what these numbers were, this number is always going to be less than this number. So now it's time to think about what we're doing. Like we got a bit lucky. I'm not sure exactly what we did, but something happened. Somehow the binary number, something happened with it. So again, to repeat what we're doing, we're trying to just use everything together. Um, we're threatening the devil by saying that I'm going to make all my zeros ones until you make a 1 a 0. And once you make a 1 a 0, everything that happened so far in that round is irrelevant, because I mean you have made a 1 a 0. So the number has reduced. Like even if this was 1 0 0 0 0 and this is 0 1 1 1 1, this number is still more than this number, because 2 to the n is more than the summation of 2 to the n minus 1 plus 2, whatever. I mean, of course, this number is just this plus 1. So um, the devil can also force us to increase the binary number. Um, why so? Like, my point is that, um, like, I mean, the devil can't really force us to do anything. Like, the devil could have forced us actually to reduce the number, but that's against his wishes.
No, like I
You're
mean,
trying to say something.
for your algorithm, we started. But what if the devil starts and follows the same algorithm which you told?
Okay,
Then we
that's a
have
valid
to
question.
we
So,
have
but
to increase.
the point is that if the rightmost digit was a 1 and the devil made it a 0, the number is already reduced. So we don't change anything. We just say, okay, nice, the number reduced a bit. And then we restart after 1. So the point is, at any point, if the devil makes a 1 a 0, we're done for that round. We'll just like wait for the thing to reset. We'll just like keep all our zeros as zeros. And if he wants to make more 1 zeros, that's even better for us. He's making the number even smaller. That's okay. But the number can't increase, because the only way the number increases is if we make a 0 a 1. And the only time we make a 0 a 1 is if we are counting on the devil to make a 1 a 0 after us. So that's the sort of idea here. Yeah. So the point is that either the devil gives in and decides that, okay, I will let you make it all once, because that's what I'm trying to do by scaring him. Or he doesn't give in and he keeps reducing the number. But if you keep reducing the number, eventually it'll become 0. Doesn't the 0 come to the first position? If it does come to the first position, that's nice. Then the first position will remain 0 forever, and we can just work with the rest. So actually, this is a very nice way of thinking about the induction. So if you can first force the left, so we have already solved the problem, by the way. We have gotten this sort of algorithm, which is just saying that until in a round the devil makes a 1 a 0, keep making a 0 once, and once he does that, relax, wait for the next round. We target the maximum, and the devil then helps us reach the minimum. Exactly. So you scare the devil by saying him that if you don't listen to me, I'm going to make it the maximum. And then the devil is like, okay, I have to That was unfortunate. I think my phone just died, so the personal hotspot died. But I think it's fine. I'll probably turn off camera so that this doesn't die off as well. Um, yeah. Yeah, Devil got upset that he's teaching us a way to items. That is true. Um, okay. So yeah, this is really the point of this problem, that you can like just like this is all coming from these basic sort of ideas that we had. The basic ideas were that, okay, probably useful to think of ones and zeros, probably useful to um, do things that are slightly, feeling greedy-ish, like things that don't feel greedy, whatever. Like you're trying to mix up a lot of different ideas and come back in some sort of thing together. Um, and yeah, so what I was mentioning there was that induction also does turn out to give a solution. And actually, this is something you guys can try and work on. It's actually not very easy to make it work. You need to induct on what's known as a stronger claim. That is, you don't just induct on the fact that it's doable for n minus one things, but it's doable in a very specific way, and then it works out. So this is some sort of like homework, and if you want, like I can share the exact solution on like Discord, so that if you get stuck again, you can maybe take a hint from that. Um, but yeah, the real reason I chose these sorts of problems was to just show you a lot of different things. Um, the first problem really showed you that this sort of base cases can literally lead you to a solution. But that's not always true. Like here, we worked with base cases for a lot of time and we got sort of nowhere. But that doesn't mean that base cases are useless. What it means is that you don't always want to find out the exact thing from the base cases. You want to start getting intuition. You want to understand what sort of things could work, what sort of things will never work. Once you start figuring those things out, they'll help you no matter what your hard technique is. Here, our hard technique was thinking of binary, thinking of increasing the number in binary. That's a very specific hard technique. But the intuition of that really comes from just like trying a lot of things. Um, and honestly, it's a little bit of a guess. Like when I tried this problem, the first thing I actually tried is think about binary and trying to increase or decrease the number. And it was a guess. It felt like maybe that could lead us somewhere. If it doesn't work, then it doesn't work, but it's something worth trying out. And that's the way sometimes it's useful to think about problems. Sometimes you should lead yourself to the solution, and sometimes um, you should just like um, try a lot of different things until something works out. So maybe a little bit of like an alpha proof way of doing it, like just trying a lot of things from your toolkit until one of them actually leads to a solution. But yeah, whatever. um, okay, so yeah, just to like conclude, what I want to say is that um, algorithms are a very sort of vast field. And of course, I didn't like get nearly enough time to cover a lot of the things that are like a part of algorithms. As like I can devote an entire lecture just talking about this specific topic of greedy algorithms. But today's class was not about that. Today's class was just about how should we approach this question. We should approach them by experimentation. We should approach them by trying to understand the problem, and then leading ourselves into some sort of different sort of approaches until something starts making sense to you. So that's the way at least I approach problems. We did have to talk about the IMO P5. So um, should we talk about it? Okay, how many people want to talk about the IMO P5? Because it's also like 8:30. So like if enough people are like ready to stay and listen, then like we can talk about it. Okay, so people are interested in the IMO P5. Okay. Um, I'll just get a copy of the problem quickly from the OPS. Community contest. IMO. Yeah. Sorry, give me a minute. Okay. Some lie that's killing. Yeah. Okay. So it's a pretty long statement. In fact, I can probably write the solution in lesser lines in the problem statement. Okay, probably not. But um, yeah, the problem here is just saying that there is this sort of 2024 plus 2023 grid. And actually, okay, this is not relevant to anything at all, but there was this interesting problem I saw some years back, which was like, question, do you think there's ever been an IMO where a number between 1959 and 2050 has appeared, and that number is not the actual year of the IMO? And this really ruins that. 2023 has appeared, and this was the year 2024. So that's funny because I actually I'd never seen an example like this before. Would like to try it first. I should be leaving so that, yeah, if you do want to try it first, then okay, someone wanted to talk about the solution to the previous one. Yeah, I think that's very reasonable to make regress, right? This point is just like, follow this algorithm until in a single round the devil makes something one, keep making things one. Once he does that, keep your things zeros as zeros. The number has to reduce in binary, so we are done. Like that's it. So could be leading to loops. What could be leading to loops? Um, like the point is, if the number keeps reducing in binary, you never get stuck in a loop, because if you get stuck in a loop, that means at some point you come back to the same number in binary, but you don't, because it keeps going down. Like if monovariant keeps reducing, you can never reach the original thing again. So that is not a problem. My name is changed to Rushil. Okay, that's good. Yeah. So yeah, if anyone does want to try this problem on their own, by the way, I would suggest that you do leave the meeting, because I would probably end up spoiling the problem otherwise. And yeah, the problem is like you have like a n+1 cross n grid. The first and the last row have no monsters, and each other row has exactly one monster. Um, so let's say this one, and this one have monsters, and you want to find some sort of path from the first row to the last row. So in fact, like if you want a slightly convoluted path, it could be something like this. So just something from the first row to the last row. And you wanted to avoid these monsters. And the point is, you can start off with the most obvious seeming path, like just go straight down. And you don't know where these monsters are, of course. But so you just give a path to the computer, and the computer will tell you, okay, stop. At this cell, you encountered a monster, so you could not reach. Restart. And then so on, until you actually reach the final. So that's really the problem. Is the problem clear to everyone, or should I? What about bounding the number of moves? Um, yes. So in the previous problem, okay, actually, this is something again you can think about. It's actually not very hard to prove that you can do it into the animals. I can again give a hint on discard, but yeah, it's a very cute sort of argument. So I don't want to. Yeah, a lot of people thought that the answer is going to be around log of 2023. But really, the point is that you should not be guessing the answer before you reach anywhere. So the way I really thought about this is like, okay, I mean, the first thing I did is try it for a 3x2 or a 4x3 and stuff, and I started getting some answers. And the first thing that I realized is that, okay, there are some conditions, by the way, that each column has at most one monster. And I think that is by far the most important in this entire problem. Because what I realized is that, let's say in my first move, I just figure out where the monster in the second row is. So I just go through the entire second row, and at some point it'll stop me and it'll say, at this cell you encountered a monster. Um, One second. Someone has a question on the maze. I'll talk about that once I finish up. So let's say this cell has a monster. Now, the brilliant thing that we have realized is that this column below it is going to be free of monsters. So that's the really important part of noticing about this problem. And how I really figured that this could be useful is just I was trying what happens for a 4x3, and I was like, okay, I figured out the monster in the first row, then I'm very clearly done. So maybe he won't let me figure out where it's in the first row. He'll let me pass to the first row. But then I was like, wait, I can just scan through the entire second row, and I can like literally force him to tell me where it is. And once you do this, the point is just I need to somehow enter this column, and then I can just go straight down. So for example, I can do this and just go down. I was like, okay, that's nice. But of course, the problem is this cell could have a monster. And then I was like, okay, we'll go from this side. And wow, that just works. And like for 5 minutes, I was a bit confused. And then I realized, okay, wait. There's the case. There's the case that it's the corner. And then what I was like thinking is, okay, what you want to do is just probably do this. But what if this cell also has a monster? So then I was thinking that maybe what you want to do then is go like this. But then this cell could also have a monster. So the real problem becomes everything along this diagonal starts having monsters. And the way to really stop things is to actually go around this diagonal and then at some point figure out. So of course, I'm skipping some details here. I'm just trying to like give the sort of story of how I motivated the solution. Um, but the point is that I just like kept trying the most natural thing at every point, and it just did work. Now, uh, that being said, why I don't like this problem is that there's an equally natural other thing you can do, which is to, instead of thinking of this directly, you can think about, I'll try to go via the middle. I'll choose the left half or the right half or something like that and try to sort of binary search this up. And that's a very intuitive thing. And it does make a lot of sense. So a lot of people tried that and then they got stuck. So I think there's a big learning from that as well, which is that I think sometimes you should be open to resetting. Like, even if you've made a lot of progress, you think you have a lot of ideas, you should just think from the start, am I sure that the answer is not just a small number? Like, the only way to be sure that the answer is log n is to first convince yourself that, okay, surely the number can't be very small. And the way to do that is to find a counterexample or something like that. But I couldn't find a counterexample. And that's why that's what sort of what led me to getting the right solution. So um the way I like to think about this problem is just um keep your mind open. Don't have too much of a bias that something is going to work or something is likely to work. Just be neutral about it, right? If it works, it's nice. If it doesn't work, it doesn't. It's equally nice. Like we learn something from it. And people keep calling it troll, and even I agree that it's not a great problem. But I don't think this problem is something you can't learn from. There is still something you can learn from this problem, and that is to um, be very open when you explore. Don't make up your mind on what is going to happen beforehand. That's what I. Yeah, going back to someone's question. I have a question about the maze problem from before. I tried thinking about how you could reverse. I don't get it. So inverting the exactly. So inverting it will not work. But the point is that you know what the maze is. So of course, if I know how to reach a point, I know how to go back. Like if I didn't know what the maze was, then I would be in trouble. But because I have listed these mazes down and at every point I'm just looking at the next maze, I know how to reverse it because I know what the maze is. So that's the key detail, if that makes sense. Okay, I think we're mostly done. I'll stop recording.